Having discussed about the DIT and DIF structures for the order 8, now let us consider the order which is 4. For n is equal to 4, a DIT structure for computation of DFT will look something like this. The number of inputs and outputs will be 4 in number, and as in the case of the DIT structure for n is equal to 8, the inputs are applied in a bit reversed index fashion. So you can see the index x of 0, next comes x of 2, next comes x of 1, and then we have x of 3. There are only 2 stages in this signal flow graph. In the first stage, the size of the butterfly is smaller, and the second stage, it is a increasing order. The real factor we are considering here is called as W4 to the power of 0, and its value is equal to 1. After we get the output of the first stage, we have to scale the lower 2 lines by W4 to the power of 0 and W4 to the power of 1. So these are the 2 real factors that we require in solving a 4-point DFT. And finally, after you get the answers, we observe that the results here will be in a sequential order. So the outputs are x of 0, x of 1, x of 2, and x of 3. On similar lines, if we observe the structure for DIF FFT, for DFT of n is equal to 4, we observe again there are 2 stages. The size of the butterfly is decreasing. Total factor multiplication is after the butterfly. The inputs are applied in a sequential manner, and the answers are generated with a bit reverse index. So this is the structure called as decimation in time FFT for DFT calculation for n is equal to 4. Similarly, we can arrive at the inverse structure for DIT and DIF respectively for n is equal to 4. The inverse structure for decimation in time will resemble the one which is shown here, or it is similar to the DFT structure involved in DIF, whereas the inverse structure for DIF will look like that of DIT, which is used in the case of DFT, with the notable changes that input is going to be capital X of k, output becomes small x of n, total factor powers will be negative, and we should not forget that we have to scale the answer by 1 by n. So these are the important differences and changes we should remember while we are solving problems based on n is equal to 4. Let us consider an example of usage of FFT and IFFT of n equals 4. This particular problem asks you to compute the circular convolution of 2 given sequence x of n and h of n, making use of DIT method of finding the FFT and IFFT. The method is very simple. First we have to compute the FFT of x of n, then we have to calculate the FFT of h of n, multiply the individual outputs, and then calculate the inverse fast Fourier transform. First, let us consider the first input x of n is equal to 1, 2, 3, 4, for which the DFT has to be calculated using DIT FFT method. Now we are aware of the structure for decimation in time. The inputs are said to be in bit reverse fashion. The output will be sequential. The size of the butterfly is from smaller to larger. Total factor multiplication is done before. Now applying the inputs x of 0, we know the value is 1. Next x of 1 is 2. Next x of 2 is 3, and the next value is 4. W4 to the power of 0, the answer is 1. So scaling will not make any difference. we can consider the same input 1 and 3. The sum of 1 and 3 we can calculate is 4, and the difference here is equal to -2. Therefore, the answer for this is 4, and 1 minus 3 will be -2. Similarly, the sum of 2 and 4 will be 6, and the difference will be equal to -2. For the second stage, we have to calculate the input after scaling. So here no need of scaling, so the input is 4 and -2. Next, W4 power of 0 is equal to 1, so multiplying will give you the same input, that is 6. W4 to the power of 1, the value is equal to -j, therefore scaling with -j gives you the answer, which is 2j. Then once again the output of the second stage is determined using addition and subtraction. 4 plus 6, the sum is 10. The difference 4 minus 6 is -2. Next, -2 added with 2j and -2 minus 2j. So these are the results that we get from the first FFT structure. Now to get the answers, the values here are corresponding to x of 0, x of 1, x of 2 and x of 3 in sequence. We can express the answer in a sequential form. The answer in the x of k is 10 minus 2 plus 2j minus 2 minus 2 minus 2j. In the second step, we have to compute the DFT of h of n is equal to 1, 2, 2, 0. This is also done using decimation in time FFT method. So as we had done in the previous case, here again we have to express the inputs x of 0, x of 2, x of 1 and x of 3, which is equal to 1, 2, 2 and 0. So there is no requirement for scaling because multiplication by W4 to the power of 0 is also, it's 1. Therefore, the inputs are taken as it is. We find sum and difference. The sum is equal to 1 plus 2 is 3. The difference 1 minus 2 will be minus 1. The sum of 2 and 0 is 2. The difference is also 2. To proceed to the second stage, we have to scale the inputs. So no scaling is performed here, but in the lower part we see we have to scale with W4 to the power of 0 and W4 to the power of 1. So 2 into 1 is 2 and 2 into minus j is minus 2j. Once again, we have to perform addition and subtraction. 3 plus 2 is 5. 3 minus 2 is 1. Minus 1 added with minus 2j. Minus 1 subtracted with minus 2j. So this is the result we get for the case, that is h of n. And the answers here correspond to x of 0, x of 1, x of 2 and x of 3. In the sequence form, you could write you could write the result as h of k is 5 minus 1 minus 2j, comma 1 minus 1 plus 2j. I should have changed the notation here as h of 0, h of 1, h of 2, h of 3 and so on, and this becomes h of k respectively. So please consider that. Next we compute the product of h of k and h of k. We have to perform element by element multiplication. So we get the answer as 50, 6 plus 2j minus 2, 6 minus 2j. Be careful when you're doing complex multiplication. The final step would be to compute the IDFT of the above product and using the DIT FFT method. Now the structure is the inverse structure for DIT that we just solved. Let us have a look at the structure now. So since it's an inverse structure, we realize that the inputs will be x of k. So applying inputs x of k, we will generate the result which is corresponding to x of n. The inputs here are in sequence. Therefore, the inputs are x of 0, x of 1, x of 2 and x of 3. The outputs are going to be produced in a bit reverse fashion. X of 0, x of 2, x of 1 and x of 3. The real factor multiplication will happen after the structure. Therefore, we have to multiply it by W4 to the power of 0 and W4 to the power of minus 1. And here we have to multiply it by W4 power of 0 and W4 to the power of 0. And lastly, the answer we get has to be scaled with 1 by 4. Now let's start filling in the numbers. We have the values. First value is x of 0. X of 0 is equal to 50. X of 1 equals 6 plus 2j. X of 2 is equal to minus 2. X of 3 is equal to 6 minus 2j. Once again, we realize we are doing addition subtraction operation. So adding the value 50 and minus 2, we get the answer which is equal to 48. Next, we have to do 50 minus 2. The answer will be 52. Next, we have 6 plus 2j added with 6 minus 2j. The imaginary part cancels. The sum is equal to 12. Next, we perform subtraction. The real value cancels and the imaginary value remains. So we get the sum, we get the difference as 4j. Proceeding to the second stage input is expressed after scaling with appropriate middle factors. So W4 to the power of 0 is 1, so you get the same value 52, and W4 to the power of minus 1 is equal to plus j. Therefore, j into j is j square, which is minus 1. So the value becomes equal to minus 4. Next, performing the addition and subtraction again. 48 plus 12, answer is 60. 48 minus 12, answer is 36. 52 plus minus 4, answer equals 48, and the subtraction results in the answer, which is 56. W4 to the power of 0 is 1, so we can ignore that multiplication. Finally, the answer has to be scaled by 1 by 4. Therefore, the result we'll get after this calculation is equal to the final answer. X of 0 is 60 by 4. The final result of the calculation is 15, 9, 12, 14. Now we have to arrange this index in the correct order. Therefore, the answer becomes y of n equals 15, first term, next comes 12, next comes 9, and the last value is 14. Let us consider the case wherein the DFT can be used for calculating the IDFT. First, we examine the equation of DFT and IDFT. We find that DFT and IDFT are structurally similar to each other. The input x of n in a DFT is changed to x of k in the case of IDFT. The trill factor Wn to the power of kn is replaced by its conjugate, which is Wn to the power of minus k in this case. The additional thing which we have is the multiplication with 1 by n. Now let us start with the IDFT equation and take complex conjugate on both sides. Now conjugating x of n gives you x conjugate of n, which is equal to 1 by n times summation k from 0 to n minus 1. The conjugate of x of k is called as x conjugate of k, and conjugating the trill factor Wn to the power of minus kn, it becomes Wn to the power of kn. Now, this equation tells us that the quantity, that is the summation, it looks very much like the DFT, except for the change that we are calculating the DFT of x conjugate of k. Therefore, the summation can be replaced by DFT of x conjugate of k. Therefore, from this expression, we learn that the DFT of x conjugate of k is equal to n times x conjugate of n. Now, from this, we understand to the DFT block, if we feed the input x conjugate of k, then the output of that particular DFT block will be n times x conjugate of n, as shown by the equation. To the DFT block, when you are providing input x conjugate of k, the answer you will get is n times, capital N times x conjugate of n. Now, since we are interested in x of n, we can do some further processing and we can get the value of x of n. So the stage is shown as follows. First, you are provided with the value of x of k. We need to take its conjugate to get x conjugate of k. Then compute the DFT of this input x conjugate of k, which we know is equal to n times of x conjugate of n. Next, we can conjugate this particular value. N is a real value, it is not affected by conjugation. The complex conjugate of x conjugate of n is x of n. Conjugate, it cancels the effect of conjugation. Now, to remove the n, we have to scale this value by 1 by n. So multiplying by 1 by n will eliminate the n and we get the value of x of n. Therefore, the steps can now be written as: take complex conjugate of x of k, compute the DFT, take complex conjugate again, and then divide the result by n. So this process can be used so that we can use a DFT block and generate the answer for IDFT. Now this is illustrated using a very simple example here. First we have to apply inputs which are x of k and they have to be conjugated. So if we are using the method called as DIT, we are aware that the inputs have to be applied in bit reversed manner. Here we will apply input x conjugate of k in a bit reversed indexed manner. Then the content inside the block is your regular DIT structure. Now after you get the answer, we remember that we have to divide by n. So every point is divided by n and the answer will be x conjugate of n. So the input applied here was x conjugate of k. The result we obtain here is x conjugate of n, from which if you want to take x of n, we have to conjugate each of these outputs. So conjugating each of these outputs will give you the expected result. Let us consider this example to verify the concept that we just studied. Compute the IDFT of x of k is equal to, the sequence is given using DIT FFT / DFT. So they are specifically saying that you use a DFT algorithm to calculate the IDFT. So the method goes something like this. As we have just learned from the exercise that the inputs are to be applied as x conjugate of k. And since it's a DIT structure, the inputs are having a bit reverse index. So applying the input x conjugate of 0, x conjugate of 2, x conjugate of 1 and x conjugate of 3, here we have the values. Now as we know how computation proceeds from there onwards, for a 4-point butterfly, the 12 factors we need is w4 to the power of 0 and w4 to the power of 1. Therefore, calculating sum and difference, we find the answer is 8 and 12 respectively. Next, the two inputs are -2 minus 2j and -2 plus 2j. The sum of these two is equal to -4, the difference is equal to -4j. Next, to generate the input for the second stage, we have to perform the appropriate scaling. So the top two values are not scaled, the answer is 8 and 12 respectively. In the bottom case, we have to scale with omega 4 to the power of 0 and w4 to the power of 1. Therefore, the answers are -4 and -4 respectively. So -4j into -j, the value is -4. Now we proceed with performing the addition and subtraction of the respective inputs. The inputs are 8 and -4, sum is equal to +4, difference is equal to -12. The input is 12 and -4, the sum equals 8 and difference is equal to 16. Finally, we have to divide the value by n. So dividing by 1 by 4 fetches you the answer x conjugate of n, and these have sequential index. So to represent the final answer, the result that you get has to be conjugated, but since the values are real, conjugation really doesn't have an effect here. So therefore, the results are obtained as x conjugate of n is 1, 2, 3, 4. Conjugating it again gives you the same answer, x of n is equal to 1, 2, 3, 4. Thank you all.